Now this is a technique that we can use for working some optimization problems. So as you can see here, the problems we'll be using the technique on are the ones that have restrictions given in some form. Here's an example. If we want to find the dimensions of the box with the largest volume, if we know the sum of the perimeters of the cross sections is 144, this is our constraint or restriction, and we'd have to write that in function form. So first I'll show you a geometric representation for what the constraints mean. In this problem we have a function to be optimized, and we have our constraints given here. Now there's a theorem that says the extrema are going to occur either at critical points or at boundary points. And we have found critical points earlier. We simply do the partial of x, the partial of y. We need to solve for the two. We need to know where both of those are equal to 0. So we solve the simultaneous equations. If we take the one on the right and solve for x, we can plug that into the one on the left and get the y. So the point 1, 1 is the critical point, and the function value at 1, 1 is 1. And here you see a graph of the constraint region that was given originally. X is between 0 and 3, y is between 0 and 2, so we get this nice rectangular region. Now this is just showing you that the point that we found, the critical point 1, 1, is indeed within that rectangular region. So then the bottom border of this rectangular region, the line along the bottom that I've got highlighted here in orange, is the line y equals 0. So if we take y equals 0, plug that into our function, we get f equals x squared. Well, here is the graph of x squared on the interval from 0 to 3. Now you see all I've done is taken the graph of the function that we had originally and twisted around so that we're looking at the xy plane. So that's the graph of, or excuse me, the xz plane, not the xy plane. So that's the graph of the function z equals x squared on the interval from 0 to 3. Now I won't go through the mechanics of finding this, just to point out that the maximum point occurs at x equals 3 and the minimum at x equals 0. So we're going to take those points, 3, 0 and 0, 0, and find the function value for each of those. Now we'll do the same thing for the top border. Notice the top border is y equals 2. So if we take our function, substitute a 2 for y, we get this. Now that's in the plane y equals 2. And so we're looking at an xz coordinate system in the plane y equals 2. We've got the parabola x squared minus 4x plus 4, which we could find the maximum and minimum value on. I'm just going to do that graphically. The maximum is going to occur here at x equals 0, and the minimum will occur here at x equals 2. So we'll take those points, 0, 2, 2, 2, plug them into our function and get the function values, and we'll make a list of these here in a moment. Here's the left border. Along the left-hand border, that would be x equals 0. Plugging a 0 in place of x, we get z equals 2y. And so here's the graph in the zy plane of z equals 2y. You can see that's a straight line. and the maximum value occurs at y equals 2, minimum value occurs at y equals 0. We'll take those points, plug them into the function, see what value we get. And the last border we want to take a look at is the right-hand border, which is x equals 3. Plugging the 3 in place of x, we get this, which is the straight line with a maximum value at 0 and a minimum value at y equals 2. So here's a list of all those points that we found. We found the point 1, 1, which was a critical point. We plugged the 1, 1 into the function and we got 1. We found these other points. We've already plugged them into the function and this is what we get. So this is a list of all of our critical points and boundary points. We pick out the largest one of those, that's our maximum, the smallest ones, which is a tie, and that's our minimum. So here's the idea behind the method of Lagrange multipliers. We'll use the f to represent the function we're trying to optimize, g to represent the constraint, and notice g is equal to some value. So if we had this optimization problem, we're trying to find the rectangle of maximum area that can be inscribed in this ellipse. We'll take a point on the corner of the rectangle, label it as x comma y. Therefore, we can write the area of any rectangle inscribed in that ellipse as 4 xy's. Now that will be the function we're trying to optimize. The constraint function is the ellipse. Now this is what the Lagrange method comes from. We have here the level curves of the function 4xy. Z equals 4xy would be a surface. I've only drawn the level curves of that surface, and I've given some of them some labels so you can see what they are. However, here is the graph of the constraint function equal to 1. And so we want to find a point somewhere where the gradient of the f function, notice how that's perpendicular to the contour lines, and the gradient of the g function are some multiple of each other. That, in essence, is the Lagrange method. Our goal is to find the values of x, y, and lambda, although we don't really care what the value of lambda is, such that the two gradients are equal. Now, the lambda, which starts with the letter L, is used to represent something called the Lagrange multiplier. So this is the method of Lagrange multipliers. We need to solve the system of equations that we get when we set the gradient of f equal lambda times the gradient of g, and when we take our constraint function. So here's a sample problem. We're trying to optimize the function x squared plus 2y squared, and our constraint function is x squared plus y squared equals 1. So we'll find the gradient of f. Here's the partial of f with respect to x and the partial with respect to y. So here's our gradient of f. We'll find the gradient of g, which is the partial with respect to x, the partial with respect to y, put together into one vector function. And then we want to solve the system of equations. Now the gradient of f equals lambda times the gradient of g means that 2x is lambda times 2x, and 4y equals lambda times 2y. We just take the x components and do 1 is equal to lambda times the other one. And the same thing with the y components. And then the constraint. So here is the system of equations that we want to solve. Although this could be pretty easily solved with a TI-89, I'll go through the hand technique and show you about solving this. If we take the top equation, we can solve for lambda by dividing through by 2x. Well, 2x divided by 2x would be a 1. Also notice that if x is 0, we get 0 equals 0. So lambda equals 1 and x equals 0 would be solutions to the first equation. Now if we take the last equation and use the x equals 0 that we found from the first one, we would get 0 plus y squared equals 1, which gives y squared equals 1, which would have the two solutions, y equals 1 and negative 1. And so we already know that we would have these possible extreme values. X equals 0, y equals 1, x equals 0, y equals negative 1. However, using the middle equation with x equals 0 and lambda equals 1, we would get 4y equals 1 times 2y. Well, the only solution for 4y equals 2y is y equals 0. If we take that and plug it into the bottom equation, we would get x squared equals 1, or x equals 1 or negative 1. And so using those values, we get our other possible extreme values. So finding the function value for each of those, the smallest would give us our minimum and the largest would give us our maximum. So we would have the maximum value occurring at 0, 1 and 0, negative 1. The maximum value would be a 2. The minimum value would occur at 1, 0 and negative 1, 0, and the minimum value would be a 1. And I went ahead and constructed a graph of this so you could see how this relates to what I told you earlier. And that is, here are the level curves for our optimizing function, a few of the level curves. Here is, in blue, the constraint function, x squared plus y squared equals 1. And here I've highlighted in colors, as you can see, at this point right here, which would be 0, 1, and at this point, which would be 0, negative 1, we have the constraint function, blue, and the level curves of our optimizing function, which in this case be the red one, that are both tangent at the same point. And we also have the point 1, 0 and negative 1, 0, where again the level curve, that would be x squared plus 2y squared, is tangent to the constraint curve.